you can see, we're beginning our discussion of power series, and you can read, but as you know, I'm going to read to you. A power series is a series of the form, the sum from k equals 0 to infinity of some expression c subscript k times x minus a to the power k. Now x is a variable just like we're used to. C sub k only is constant, except it changes every time we have a new k value. And of course a is a constant. So this is called a power series centered at a, or about a, and that's this a that's being subtracted from x. And then these c sub k's are called the coefficients of the power series. That's because when you write it out, basically we have a polynomial where these end up being the coefficients for each time we change the power. Now, because we have this variable x in it, we can define a function in the following manner. We could say f of x is equal to that series. So the idea is when you put an x value in here, then we replace that x here, of course, and we have a series. So for every x value, there is a series. And the sum of that series then is in fact the value of f of x. So it's quite complicated, and obviously not all, maybe not for any x. There's some x's where the series might not converge, so it wouldn't have a sum. But we're assuming here, of course, we're talking about those situations. So of course, that x is the variable of the function. Everything else is fixed. Every time we have a new value of x, we have a brand new series to calculate the sum of. So there could certainly be this question asked about what is the domain of this function. That's a reasonable question. Well, the domain, of course, is the set of all x values for which f of x makes sense. So all the different x values for which the particular series for that x converges. And that set of x values we call the interval of convergence. So rather than saying the domain of f, what we talk about is the interval of convergence for this power series. This is called a power series. It's called a power series, of course, because we have x's, the power on the expression involving x is increasing one after the other. Well, let's move on to see what else we can learn about these, and we define something that's called the radius of convergence, which helps us decide what this interval of convergence will be. Okay, the radius of convergence determines the interval of convergence, or the values of x for which the power series converges. Well, the radius of convergence we indicate by a capital letter R, and it's a number for which all x values that satisfy the inequality, absolute value of x minus a, is less than r. Okay, that means any x that satisfies this inequality is in the interval of convergence, or in the domain of the power series. Now let's investigate, and let's make sure we understand. Let's make sure we understand that the absolute value of x minus a being less than r means that x minus a is in between negative r and positive r, whatever x minus a is. Remember, a is the center. A is a number that's specific to a particular power series called the center, and so x minus a then has to be between negative r and positive r. So if we solve this inequality for x, we just add a all the way through. So the interval of convergence, there's the set of all x's, so that x is bigger than a minus r, the radius of convergence, and less than a plus r, again, the radius of convergence. So take the center and subtract the radius of convergence, take the center and add the radius of convergence, and it's the x's in there. And I've illustrated that here in this fashion. See, here is the a value, the center, and if we move r units to the left of a, we have a minus r, and if we move r units to the right of a, then we have a plus r. And so that's a good indicator of the reason a is called the center of convergence, because it's the values of x's that are in this interval for which this power series converges. And so A is in the center of that interval of convergence. We move from the center r units to the left and to the right to get the entire interval of convergence. So those pieces make sense as we see them put together there. Well, what I want to do next is show you how we calculate the radius of convergence, because that depends on, that tells us the rest of the story and lets us calculate the interval of convergence. I'm probably going to do this a little differently than the book, or certainly my math lab does, but it's very important, I think, it helps you in this process rather than have to rethink things every time you work on a problem. This is a repetitive idea. So let's look at how we can do that. So we're going to find the values of x for which this series converges, and we're going to do that by using the root test for convergence. And what I mean by that is, remember what the root test convergence of a series is. We take the limit of the absolute value of the kth term divided by the k plus first term, that is, divided by the kth term, or maybe we said n plus first term over n term, the absolute values of those. And so the kth term of this series is this whole expression here, and the k plus first term would just be c sub k plus 1 and k plus 1, okay? So those are the, here we see then, if we want for this series to converge, it must be true that the limit of the absolute value of the k plus first term divided by the kth term is going to be less than 1. So if that is true, then the series converges. Now, by the same token, and I'm going to remind you of this later, if that limit is greater than 1, then the series would diverge. And so this really is telling us exactly when the series converges and exactly when the series diverges. And so if it doesn't converge somewhere, then it diverges. That's kind of a little bit of simplification of what we're really doing, but that gives us the idea. So what I'm going to do is I'm looking at the limit of this absolute value. Now, of course, we could think of this fraction as the c sub k plus 1 over c sub k times the fraction x minus a to the power k plus 1 divided by x minus a to the power k. And so we have the limit of a product, which is the product of limits. So I've just broken it down on the left side to the limit of the first fraction multiplied with the limit of the second fraction, thinking of these two fractions multiplied together. So that still has to be less than 1 for this series to converge. Now, what I've done, if you'll look here at this expression, we just have one more power of x minus a in the numerator than we do the denominator. And so this ends up just being the absolute value of x minus a, this fraction. And so we're in this is the limit then of the absolute value of x minus a. And so this still has to be true for the original series to converge, for it to pass the root test for convergence. And that's what we're wanting, to make sure that it's passing the root test so we know it converges. Now, obviously, or maybe not obviously at the beginning, that as k goes to infinity, the absolute value of x minus a is not changing at all. That's just a constant in terms of k changing. And so the limit of the absolute value of x minus a as k goes to infinity is just the absolute value of x minus a. So that's all I've changed here. So once again, this inequality has to be true in order for the series to converge. Now what I've done is I've just divided both sides by this limit, so I have the absolute value of x minus a alone, okay, on the left side by itself. And then I make an observation that this is the same thing as the limit of 1 over c sub k plus 1 divided by c sub k, because in that case we'd take the limit of the numerator divided by the limit of the denominator. So I'm just rearranging a little algebraically. Now, in this expression, 1 over c sub k plus 1 divided by c sub k is nothing more than c sub k divided by c sub k plus 1. So the absolute value, so here's the idea then. The absolute value of x minus a must be less than this limit for the series to converge. See, that was the whole thing. For the root test to ensure convergence, then all along we followed that this inequality has to be true. Now, of course, if it was greater than this limit, then the series would diverge for those x values. Okay. Now, so notice I put this equal r, and that's just kind of out of the blue, because that's exactly the definition of what the radius of convergence is. And so actually that's how we calculate the radius of convergence, is simply by calculating this limit of the kth coefficient divided by the k plus 1 coefficient. Now remember, that's not the entire piece. That's just this part of that series, okay? And the rest of it kind of came out into the wash. So R, this is how we calculate R, is what I'm trying to spit out here. It's the limit of the absolute value of the kth coefficient divided by the k plus 1 first coefficient. So our power series converges provided the absolute value of x minus a is less than r. See, that's all we've got up here at this stage. That's when our power series converges. Well, let me see if I can get several pieces out here all at once. I know there's a lot to read here. So let's kind of rehash what I just said. So what we went through, here's the way we calculate R. Right here's the way we calculate R. It's this limit. Now, the power series converges if the absolute value of x minus a is less than R. The power series diverges if the absolute value of x minus a is greater than R. And if the absolute value of x minus a is equal to R, we don't know whether it converges or not, because this refers to just exactly the endpoint. See, when this would happen, when x minus a is equal to r or negative r. And so that boils down to being these two endpoints. See, here's the center A. Here's the radius of convergence. So we go to the right r units, we go to the left r units. And so in this green area, see, this is where the absolute value of x minus a is less than r. This green area is the interval. We know that it converges in the green area. In the red area, that's where the absolute value of x minus a is greater than r. So it diverges if we're outside this interval. Now, the only thing that is the question mark is at the endpoints of the interval itself, at a minus r or a plus r. That's what this is referring to. We haven't, that would be when the root test gave us a value of 1. And remember, when the root test gives us did I say the root test way back up here? Oh my goodness. That's the ratio test, isn't it? Not the root test. You've probably been wondering what I'm talking about. That's the ratio test, not the root test. Okay, so remember the ratio test, when we get a value of 1, then it's undecided. We don't know. It might converge or it might not. It just does, the ratio test doesn't tell us anything. I'm still feeling bad about me saying that was the root test. So that's the only issue here. We're for sure know that it converges. The power series converges on this interval. So we know the center, and if we go to the left, if we subtract the radius of convergence, and if we add the radius of convergence, we know that it's for sure converges in that interval. And so this is just stating that another way. The power series converges as long as x is between a minus r, and remember a is the center, and a plus r. And remember how we calculate r. R is the limit of the absolute value of the ratio of the kth coefficient divided by the k plus 1 coefficient. That's very critical. This is really why I've highlighted that. That's important. Now, this test doesn't tell us, this R doesn't tell us about whether we actually converge at these endpoints. So we must check the endpoints separately. That is, we must find out whether it converges at this endpoint and find out separately if it converges at this endpoint. And it might not converge at either endpoint. It might converge at both endpoints. It might converge at one and not at the other. We don't know that in advance. We just have to test and check. Let me summarize it again on the next page. Actually, not so much a summary as an indicator of what kinds of R's we can have and what it means, radius of convergence. So we're given a power series. Remember, the C sub k's are called the coefficients of the power series. So we're given a power series, and we're asked to calculate the radius of convergence. And so this is the way we calculate the radius of convergence. It's based on these coefficients of the power series. Now, it's kind of putting these pieces together. When we calculate R, the radius of convergence, if it's equal to 0, that means the power series converges for only one value, and that's when x is equal to a. So the function would not be very important, would it? There'd be only one good value of x in the domain, only one x. Now, if R is a positive finite number, and it will always be positive, so that's not really an issue, because obviously we're taking the limit of an absolute value, aren't we? So if R is a finite number, then the power series converges for all x's between a minus r and a plus r. Okay, and we can write it as an interval like we've done here, or as above like I've done there. Now, it could be that when we calculate this limit, we get infinity. And so the radius of convergence would be infinity, which means the power series converges for all x values. That's what that means. So, and that can certainly happen. Okay, could have a power series that converges for any x value that we can think of. Now, the interval of convergence of the power series is this interval from a minus r to a plus r, plus maybe the endpoints included. See, that's what we said before. So far, we just know it converges between those two numbers, but it might converge at a minus r, which then would put a bracket instead of parenthesis, or it might converge at a plus r, which in that case would put a bracket instead of a parenthesis. But those we have to check separately. So we have to decide whether the series converges for this x value, or if the series converges if we have this x value. And so we need to see how that plays out when we're doing a problem. Well, I guess it's time that we ought to look at an example to see how this plays out. Okay, so here we're to determine the radius of convergence and the interval of convergence for the power series, the sum equal k equal 1 to infinity. And then notice it's a 1 instead of a 0. That's not really a big deal, so let's not get too worried about it. And we have negative 1 to the k power times k divided by 4 to the k power, and all that multiplied by x plus 3 to the k power. Of course, this is the variable part, the x part, and of course all of this is changing, of course, as k changes. So this is the coefficient of the power series. And notice this has, rather than an x minus a, rather than minus, this has an x plus. And that really means we're just dealing with x subtract negative 3, doesn't it? So we shouldn't be worried about that either. Now, what I really started with here is just to give an illustration of what this power series looks like. And it's basically an infinite polynomial. All I've done is start at k equal 1, and then k equal 2, and k equal 3, and k equal 4, and of course it goes on forever from there. So it's really just an infinite polynomial, isn't it? That's all it is. And we would like to know when that infinite polynomial, for what x's that has a value and what x's it doesn't have a value. That's what we're talking about, the interval of convergence. When does this make sense and when does it not make sense? Because every time we change x, we've got a new series. We've got a new infinite sum. So we have to first, to find the, well, first we're going to find the radius of convergence, but we always need that first before we find the interval of convergence. And so we've got to identify what our C sub k's are, the coefficients. And the C sub k's is this expression right here, the part that doesn't involve x. So it's this expression right here. And of course we need that if we're going to calculate r. Remember, the way we calculate r is with this limit. It's very close to the ratio test, doesn't it? Except in the ratio test, then to find out, that's not actually calculating r, that's calculating whether the series converges. And in that case, we have actually the inverse of this, the reciprocal of this fraction, don't we? Okay, so it's a little different, but very similar, because we actually use the ratio test to make this decision. So here we go to set it up. And I've done a couple of things right away. Really, we have the absolute value, but everything is positive except this negative 1 to the power k. And so when we had absolute value, that negative 1 to the power k ends up just being positive 1, so it's no big deal. So C sub k, you can barely see that division bar, but C sub k, after I take the absolute value, is just k over 4 to the power k. And C sub k plus 1 is just k plus 1 over the 4 to the power k. Okay, so it's just a pretty quick act there. Now, when I look at this, and you can verify it, we're going to reciprocate here. And so we'll have we'll have 4 to the power k plus 1 times k in the numerator, and 4 to the power k times k plus 1 in the denominator. And 4 to the k plus 1 over 4 to the k is just 4. So we have the k in the numerator and the k plus 1 in the denominator. And when we calculate that limit without any great fanfare, I mean, I'm convinced you can do that easily, we get a value of 4. So the radius of convergence is 4. So what? What does that tell us? Well, that means that the series converges anytime that expression that involves x minus a, or in this case x plus 3, whenever that's less than the radius of convergence, which in this case is 4, then that's the beginning of our interval of convergence. So the radius of convergence then helps us determine the interval of convergence. So that means x plus 3, see, if this is true, x plus 3 has to be between negative 4 and positive 4. And so all I'm doing now is I'm taking this inequality and solving it for x. So I subtract 3 all the way through, and I get this inequality. Of course, negative 4 minus 3 is negative 7, and 4 minus 3 is positive 1. So this power series converges for all x's between negative 7 and 1. Now, the only thing we don't know, and it converges outside that interval, the only thing we don't know is, does it converge at negative 7 and does it converge at positive 1? So that's what I'm talking about when I say we have to test those separately. And so that's what we're working on next. We know it diverges as long as we're less than negative 7, and it diverges as long as we're greater than positive 1. But at negative 7 and 1, we don't know about convergence or divergence at all. So we will we'll continue this on the next page. And of course, as I was saying, we've got to check those endpoints separately. So as we move to the next page, so to check the endpoint x equal negative 7, we need to know if the series, the original series, converges when x has the value of negative 7. I mean, after all, here's what we're trying to find out. For what values of x does the series converge? And see, every time we change x, there's a new series. So which ones of those converge? And then we want to know, does it converge at the endpoint, negative 7? So we replace the x in the series with the value negative 7. And then we check to see whether that series converges or not. So when x is negative 7, then our series, all I've done is I replaced my x with negative 7. And so inside here, I actually have a negative 4. So our series becomes this summation. Now we need to know whether that converges, if that has a finite sum or not. Now we need to do a little algebra before we are going to get this accomplished. And notice what I've done is I've taken negative 4 to the k power and written it as, I thought of it as a negative 1 times 4 all to the k. So that'd be negative 1 to the k times 4 to the k. And then negative 1 to the k times this negative 1 to the k is just going to be 1 to the k. I mean, that's we could look at that several ways. Either they're both positive, which would be positive 1, or they're both negative. When we multiply together, we'd get positive 1. So those kind of go away in the thought of things. And so then I have a 4 to the k power times k over a 4 to the k. So the 4 to the k's cancel, and I'm left with just k. So the sum from k equal 1 to infinity of k is certainly infinite. It's just growing unboundedly, isn't it? So that tells us the series diverges when x is negative 7. It does not converge. And so negative 7 is not part of the interval of convergence. It's not the one of numbers that converges for. Now, we're going to go through the same process for when x is equal to 1. So we replace the x with 1. So that's what goes right here. And now we have a 4 in that position. Okay. And so I'm just going through the process. I need to know whether this series converges or not. And so I'm simplifying it as much as I can. I have 4 to the k over 4 to the k, which goes out and leaves me just this negative 1 to the k times k as my terms, okay, as my term. Now, I claim that sum does not exist, so the series diverges. And obviously, if we look at it, what we're doing is we're taking, for instance, a negative 1 and then adding a 2, and then subtracting a 3 and then adding a 4, and then that's what's actually going on there. We're adding integers together, but they're alternating in sign. And it's going to, our sum is going to go from a number to 0 to a number to 0 to a number to 0. It's not getting close to anything. But we could also use the divergence test, remember, look at the limit of the terms of the series. And in this case, that would be the limit of negative 1 to the k times k. And you'll notice that as that goes to infinity, that's not getting close to 0. And so that tells us that it diverges in another way. So here's what we know then. We know that since this limit does not exist when x is negative 1, then we know the series, as I've just said, diverges as x equal negative 1 as well. And so that tells us that the interval of convergence does not include the endpoints, and so the interval of convergence is exactly what we see here written, and we could write that in interval notation as well, but it does not include the endpoints. Very important idea. I think I've got another example here I'd like to go through. Let's see what we've got. Oh, yes. Find the interval of convergence for the power series, the sum from k equal 1 to infinity of x to the k power over k squared. Now this obviously looks a little bit different because we don't have that binomial over here to the right. And so before we go very far, we have to think through a few things. We've got to stop and look at this. In this example, see, we don't, our x minus a is really x minus 0. In this example, our center a is 0 as opposed to some other number. And the c sub k, now remember, the coefficients don't involve the x portion, okay, the variable portion, the x portion. And so c sub k is just 1 over k squared. So we could think of this as the sum of 1 over k squared times, in parentheses, x minus 0 to the k power. But of course, we don't need to write x minus 0. That's the reason we just write x to the k power. And we might as well simplify that so it's not so complicated and have that in the numerator. So that we have to go through that process to think that out because it looks a little different than the ones we've had previously. Now, of course, to calculate the interval of convergence, we need the r value, which is the radius of convergence. That's critical. And so r is the limit of the absolute value of the ratio of c sub k divided by c sub k plus 1. That's the reason it's important to identify c sub k. Now, as we had a while ago, I mean, k is only positive, and so absolute value is not really adding anything to this. So we have the limit of 1 over k squared divided by 1 over k plus 1 squared. And then we just do a little algebra there. We basically invert and multiply. That is, when we multiply by the reciprocal when we're dividing, don't we? The reciprocal of the divisor. And so this expression that we're taking the limit of ends up being k plus 1 squared over k squared. And I'm not going to belabor the point, but that's going to be easy for you to check that that limit is 1. And maybe you can look at it and decide that limit is 1, but that certainly is going to be the case. So I didn't give all the detail here, but I know that you can calculate that limit to be 1. Now, here's what that tells us. Remember that this series a power series converges as long as the absolute value of x minus a is less than r, which is the radius convergence. In this case, we decided a was 0, and r we just calculated to be 1, so that's when the absolute value of x minus 0 is less than 1, or it's just the absolute value of this x, isn't it? Less than 1. It converges when the absolute value of x is less than 1. And that means x is between -1 and +1. That's what that tells us. Now, we know it converges in between. Does it converge at the endpoints? It converges outside the interval, but does it converge at the endpoints? And so we need to check the endpoint x equal -1, and we need to check the endpoint +1. Remember, what are we checking? We're checking whether this series in blue, that's the original series, converges when x is -1. So all we're doing is replacing x with -1. And I'll tell you quite quickly, it would not be hard for you to check, and this is something you do in your problems. Don't make an assumption, but this is an alternating series, and it passes the alternating series requirements, and still, since it does, that series in fact actually converges. So we know it converges when x is -1. Now, what about x equal 1? Well, when x is equal to 1, we replace x with 1, so we just have 1 to the k in the numerator, and 1 to any power is 1, and so it's this series, the sum of 1 over k squared, which of course is a p series, isn't it, where p is 2, so we know it converges. So the series converges if x is -1, it converges if x is +1, and we know it converges in between. So the interval of convergence includes the endpoints -1 and +1. And so we would say the interval of convergence is as we see it here, or in interval notation with the brackets instead of the parentheses. Now, let me pause here just for a second, that what we've shown, I've shown 2 examples. One in which it doesn't converge at the endpoint, so the interval of convergence does not include the endpoints, and the second one where the interval of convergence does include the endpoints, but we check those separately. It's possible that it can converge at one endpoint and not the other. You just have to test and see what kind of series you've got, and then use the appropriate series test for convergence. So we're using what we've already learned previously. We're just using it more frequently now. Well, this is the introduction to power series and radius of convergence and interval of convergence, and we'll do some more with power series, but that's in another discussion.